All right, let's get right into it. We are going to talk about a process that has shaped global power for, over 70 years now? And yet it's still one of the world's most guarded, most intentionally confusing secrets. This is the story of uranium enrichment. So it all starts with this absolutely incredible fact. Inside a rock, just a rock that looks like any other, there is a mind-boggling amount of power locked away. But here's the catch. In its natural state, it's pretty much useless. To get that energy out, you have to do something that is way, way more difficult than it sounds. And that really gets us to the core mystery, doesn't it? Why is this whole thing so secret? It's not just because the engineering is hard, and trust me, it is. It's because the knowledge itself is considered dangerous. The very same process that can light up our cities, well, it can also be used to build the most destructive weapons humanity has ever created.
Okay, so to really get why this is so hard, you have to understand the basic problem. And this isn't a chemistry problem, You can't just use a filter or dissolve something to get what you want. No, this is a physical sorting problem on an almost unimaginable scale. See, when you dig uranium out of the ground, almost all of it, like 99.3%, is this stuff called uranium-238. It's stable, and for what we want to do, it's basically dead weight. The real prize is uranium-235. That's the fissile stuff, the atom that can actually be split to release all that energy. But look at this chart. It's less than 1% of the total. We're talking about finding just 7 special atoms for every 1,000. That is the needle in a haystack problem we're up against.
And here's the real kicker. Chemically, these two atoms are identical. They behave exactly the same way. The only difference between the useless one and the incredibly powerful one is 3 neutrons. That's it. That tiny, almost non-existent difference in their weight is the only handle we have to separate them. So how in the world do you sort atoms based on a weight difference you can't even see? Well, you build one of the most incredible, high-precision machines ever invented, a kind of supersonic sieve called the gas centrifuge.
Now, before you get to the cool part, the uranium has to be prepped. It's mined. It's crushed into this stuff called yellowcake. And then, and this is the critical part, it's converted into a gas, uranium hexafluoride.
And this gas is nasty, it's toxic, it's super corrosive, but turning it into a gas is the only way to get the atoms moving fast enough to be sorted. So this machine, this is the heart of the whole secret. The easiest way to felt about it is like a super fast merry-go-round. You pump that uranium gas inside this tall cylinder and spin it. The slightly heavier U-238 atoms, they get flung out towards the wall, while the slightly lighter U-235 atoms tend to hang out a little closer to the center. And when I say fast, I mean it's hard to even comprehend. We're talking speeds of 60,000 revolutions per minute, sometimes even more. The outer wall of that spinning tube is moving faster than the speed of sound. To put that in perspective, that's over 100 times faster than your car's engine at its absolute redline. The engineering required is just insane. Okay, so you've got this incredible machine, spinning at supersonic speeds, handling corrosive gas. You'd think the results would be pretty dramatic, right? Well, here's the brutal truth. After all that effort, one trip through one centrifuge barely moves the needle. The concentration of the good stuff, the U-235, goes up by a tiny fraction. This is why you can't just have one of these machines. You need thousands. And this is the most important point of all. To get to the 35% concentration you need for a nuclear power plant, you have to build a factory the size of a town. You link thousands of these centrifuges together in these long chains called cascades, and you run them for months. But what if you want to make a weapon? That needs 90% concentration. You don't need a new technology, you just keep the machines running longer. That's it. So you can see why this is so politically sensitive, right? This dual-use nature of the technology means that once a country figures out how to make reactor fuel, it basically has the keys to the kingdom for a nuclear weapon. So let's take a look at who's actually in this very exclusive club. Yeah, the secret did not stay secret for very long. After the US proved it could be done back in the 40s, the genie was out of the bottle. Sure, treaties were signed to try and control it, but the knowledge leaked out. The big one was in the 1970s, when stolen blueprints from Europe pretty much handed Pakistan its nuclear program. Fast forward to today and the basic physics, it's all public knowledge. The real secret isn't how to do it anymore, it's how to do it on an industrial scale without anyone noticing. And this list really shows you how far that knowledge has spread. You've got the original nuclear powers, of course, but the list has gotten a lot longer. It includes countries that have big civilian programs, but also nations like Pakistan, India, and Iran, whose work keeps international watchdogs up at night. This right here, this is the fact that absolutely terrifies arms control experts. The hardest part of this whole journey is going from that natural 0.7% to the 5% you need for a reactor. Once you've built the gigantic, complex, expensive factory to do that, going the rest of the way to 90% is, relatively speaking, the easy part. It becomes less of a technical problem and more of a political one. But as more countries think about building nuclear power plants, the question becomes, where do you get the fuel? And that supply chain is complicated. Right now, one country absolutely dominates it.
Russia controls nearly half of the entire world's enrichment capacity. That creates a massive geopolitical vulnerability for any country that wants to use nuclear energy to fight climate change, or just secure its own power grid. And so here we are at the heart of the problem. We have this incredible tool that could seriously help us decarbonize the planet and provide stable, 24/7 energy. But that tool is fundamentally inseparable from the technology of mass destruction.
Every new enrichment plant we build for peace also makes it a little bit easier for someone somewhere to build a bomb. It's a brutal choice between energy security and global security. At the end of the day, that's the question we're all left with. The physics doesn't care about our plans. Those centrifuges will spin and separate atoms whether we use the end product to power a hospital or to build a warhead. A choice made by people and by governments. So as we look to the future, the most important question of all might be, who gets to make that choice?
That difference isn't a physical one. It's not scientific. It is a choice.